is some gigantic organization.
Right. I mean, the notion of data set identifiers is an observatory can uniquely identify their data, and then authors can embed those LaTeX macros in their AAS manuscript. ADS can then scrape
So is this
out.
in the AAS manual? Is this official?
Yes. Yes.
Okay. Welcome. I'm pleased to see you here. I understand that something like 7 hours of astrostatistics is something that few people want. I'm impressed that there's so many who do want it, and others may be on the webcast. This morning, the next hour is going to be what is often called data mining. And I'm going to show some slides, and then we're going to go through this particular script called 5_clustering classification R text. So you should have that ASCII file available in a few minutes when we do that. So let me go through some lecture, if you wish, ahead of time. If we could lower the lights, please, that would be useful. Thank you. Okay. Whoops. Astronomers have been classifying things, celestial objects, since the ancient Greeks, who separated fixed stars and roving stars, since shortly after Galileo, when nebular objects were identified. Comets were classified in the 19th century. Stellar spectra have been classified in the 20th century. Oh, be a fine girl, kiss me later tonight. Did I?
Supposed to use that, Eric?
No,
not PC.
Girl or guy. No, it's quite a yes. Yeah. That, of course, came from Harvard. And Hubble, who was in California, did galaxy morphology. It goes on and on like this. All of these classifications, to my knowledge, every single one of the classical classifications in astronomy were made heuristically, in the sense there was no mathematical tool that was applied. It was done by intelligent people looking at the properties and separating them in their minds. And the human mind is actually pretty good at it, but it's not quantitative. In statistical parlance, these are unsupervised clustering of heterogeneous multivariate data sets, where you have all these different properties that you're trying to assimilate into classes. So there are some algorithms that have been used for clustering. The most famous one is the percolation algorithm, or friends of friends algorithm, developed by Turner and Gott, Harvard, 1976. You guys are right in the middle of, heuristic methodologies, okay? These are not actually, this one is not, this one is an algorithm. Here is the algorithm for finding friends of friends. I'll mention it again later on this afternoon as to why it's not considered to be appropriate for most purposes. What statisticians have done is to consider the problem from a methodological point of view. There's no prior knowledge of how many classes are present. There's no prior knowledge of the morphology, the shape in, let's call it P dimensions. That's the dimensionality of the problem. There's no knowledge at all. And because there's no knowledge at all, please be aware that non-parametric clustering algorithms, the results are very, very algorithm dependent. It's dangerous to root your science on any of these algorithms, okay? Because the results there's a very subjective element to choosing the algorithm and choosing where to make the cuts. There's no probabilities associated with non-parametric algorithms, but there are with parametric methods. I actually showed a parametric method in my science lecture yesterday. I showed a mixture model of isothermal ellipsoids applied to a spatial point process of star clusters. And that one does have probabilities if the model's right, if you assume everything's an isothermal ellipsoid. But these are the large classes. There's agglomerative hierarchical clustering, one of which is the friends of friends. There's k-means partitioning. It has some theorems, but is still algorithmic. And the computer scientists of the 1990s developed a variety of density-based. And I'll show you a couple of these in a few minutes in R. But please be aware that this is actually, it's just an uncertain, intrinsically, there's not enough information to make it a real sort of quantitative statistical problem. Now, if you have supervised classification, although everything's really different, it feels different. Supervised means, from an astronomical point of view, as follows. You or your colleagues or your predecessors have studied the brightest and nearest members of a class that everyone agrees is a class, of RR Lyrae stars, or of Seyfert-2 galaxies, or of class 0 protostars. And these, the properties, the P properties, the P columns of your table, become very well established for the training set. And then you can apply it to a heterogeneous group of objects that might include these classes. That's called the test set. So the application of multivariate training sets to test sets is much more information. You know how many clusters are there, and you know in P space where they lie, at least to some degree. So this means that there's an enormous amount of methodology developed mostly in the 1990s and the zeros, mostly by computer scientists rather than statisticians, although there's a close link between the two. That are very important. Now, as with clustering, you have both parametric methods and non-parametric methods. The parametric methods assume almost all the time that it's multivariate normal distributions. This means that they're Gaussian in p-dimensional space, let's say 10-dimensional space. But that's actually a big family. I mean, it allows cigar shapes and pancakes and hyperspheres, and you can be hypersphere in some dimensions and pancakes in other dimensions. So it's actually quite a flexible family. But, of course, it has to be Gaussian in shape. So there are non-parametric methods that do not make that assumption. And altogether, many of these classification techniques go under the rubric of data mining. But data mining also includes the rubric of regression, multivariate regression that I mentioned last time on Wednesday. That's when you know a response variable. Okay? And so you have different problems. Regression problems and classification problems, but they're actually related, and sometimes even the same methods can be used for both aspects. In fact, often you want to go back and forth let's say you have a heterogeneous table of, let's just say, a million rows and 10 columns, and you do a regression. You say, okay, the 7th column is my response variable. I'm really interested in it. And you end up with a nice regression line that might actually not be, it may link to classes. With nothing in between. It may not actually be a physical relationship. So then you really want to cluster them first and classify them first, and then within one class, maybe do regressions. So you go back and forth between regressions and classification when you don't really know what's in your data set, but you do have supervised, you have training sets for supervision. Okay, now this whole issue has become hugely important. You know, when we did C4II galaxies and stellar structure classifications, we did it sort of just with our human mind. But now we have these astronomical wide field surveys. We make surveys in radio astronomy and X-ray astronomy, but particularly the wide field surveys in optical astronomy, with this kind of pan-stars and DES and LSST and LAMOST. These are huge projects. They're actually big data projects. So there's petabytes and even exabytes involved. And the problem is that stars and galaxies and AGN are all mixed together, and even asteroids are all in the same data set. And classification becomes essential before you even begin to do science from these wide field surveys. Okay. Let's now learn a little bit of what statisticians and computer scientists have done on supervised classification. Well, R.A. Fisher himself, using multivariate normal assumptions, showed that you can separate two classes by putting a hyperplane in 10 dimensions that draws them, and he wrote down analytically the function, the linear relationship. It's closely related to principal component analysis. It's called linear discriminant analysis. And basically what it does is it minimizes the intercluster variances and maximizes the between cluster variances, and that's what it does. That's called LDA. Okay? Non-parametric procedures, there's a sort of algorithms from the 1950s and 60s called the perceptron, and they really didn't get developed into classification tools until backpropagation was sort of invented in the 90s, and now that has evolved into something called artificial neural networks, and a simple version might be called Bayes networks and naive Bayes classifiers. Support vector machines are very important. A really brilliant mathematician named Vladimir Vapnik developed them over many decades, first in Russia, then in the US. And it's a very powerful generalization of Fisher's LDA. It actually embeds the data in maybe 10 dimensions into a higher dimensional data set, does the cut there, and then brings it down, and allows funny shapes. It involves kernel smoothing as well, and soft margins and misclassifications. It's a very brilliantly elaborate technique that's very, very powerful. Now, a completely different approach, which is actually more familiar to the astronomer, was developed by Leo Breiman, recently passed away from UC Berkeley, called CART, Classification of Regression Trees. Very widely used in the human sciences, social sciences, and business, and actually done intuitively by astronomers, but not using the algorithms. It basically says, okay, we're just going to make a series of decisions. We're going to take the first dimension. We're going to choose a dimension and just draw a line that separates the two classes, and then another dimension and draw a line. It's like boxes in color space or regions in sort of variable ratio space, things like that. We do that quite often in astronomy. But he developed a very elaborate algorithm for choosing which cuts are most important at any time and making a tree where the branches are all defined mathematically according to some criterion of the least impurity of the resulting split. And then to aggregate these and using the bootstrap to sort of test which branches and twigs are most stable and conglomerate things. Very elaborate, very, very effective method, particularly when brought together with bootstraps in a technique called random forests. So random forests and support vector machines, Google those names, you'll find millions of hits. ADS them, you'll find dozens of hits. We're not using the latest methods of supervised classification nearly as much as we should. And they were developed, let's just say roughly in the 1990s and zeros. So they're relatively new. You couldn't have learned them in college, let's say. They're new. Okay, there's an older one called K-nearest neighbors, and I'm a little disorganized. Here's artificial networks again. KNN is a very simple algorithm. It has no mathematics behind it, and it actually can work very well. So you're going to see some of those starting in 2 minutes. We're going to do it, okay, with R. So here's a little quip. The word classification appears in 1/3 of astronomy papers. We really care about classifying things. We're like, oh, that's a blue star. That's a red star. We're still doing that the same way our ancestors did. So we're looking for patterns in complicated situations in the sky and in parameter space. And yet, most astronomers are still using heuristic procedures. They're not using traditional ones like KNN and linear discriminant. And they're not using the new ones like SVM and CART and random forests. So it's not that hard. You're going to see, we're going to do it all in a few minutes now with R. You have to learn a bit. If you want to start learning, I would read Wikipedia or a chapter in our textbook. And, just to get a feeling for it, and then I'd pick up a textbook. Go to Barnes & Noble and read a book if you really need to know about modern classification techniques. Often the textbook will be called data mining. In fact, the new data mining book for astronomers covers it also, by Ivichik, Gray, and colleagues. So it's not that hard. It's not that hard to learn. It's maybe hard to judge exactly the right thing to do. But this is a very, very high opportunity sort of problem where astronomers can really improve their performance of classification if they're still doing it by heuristic means. Any comments on my very brief lecture on clustering and classification? Caution about unsupervised clustering and welcome to classification. It's really, really great. Yes, Vinay.
One of the big problems with all these methods has always been the lack of an uncertainty. Right? Do you have any comments on how people are trying to deal with that?
Okay. I happened to meet a computer scientist once, and I said, I'm going to buy you dinner. He was the founder of AdaBoost, I think, or one of the major methods of classification. A professor of computer science, distinguished in this area. And I sat him down and bought him dinner, and I told him all about our measurement errors. I said, each variable has its own each cell, each object in each variable has its own personal known measurement error. And so therefore, if it's an outlier from class number 3, some of it might be a real outlier with small error bars, but it might just have huge error bars. It's not an outlier at all. And he had never heard the problem, which flabbergasted me. I mean, every physical scientist, these people, darn it, they keep on talking to human scientists. There's no measurement error from economics, okay? Or sociology or politics. It's just awful. So actually, he didn't have an answer. This is a few years ago. Now, if you go read the IEEE and you look into the research literature, that's fairly recent. I think I see a little bit of it. Maybe Victor Pankratios, a computer scientist, might comment on this. But maybe there's some forefront classification techniques that are beginning to take into account measurement error. But basically, it's not there in the standard methods. It's not there in CART. It's not there in SVM. Well, what they really say is, look, variance is variance. If your variance is because you measured it lousy, the variance is because the quasars are jumping around, it doesn't matter to the method. So it's not as though they don't take advantage of variance. They do. What they don't do is they don't separate it into two kinds of variance. Now, the statisticians can in regression, where it's called measurement error models, and Brandon Kelly's 2007 paper is an example of that. But in classification, it is not really in prime time yet. And we should be paying computer scientists to develop these methods for us, to refine their methods for us. So we don't pay, they don't do. Okay, can you please, those of you who have laptops who are interested, others can sit by and watch me do it. I'm going to go fairly fast. I'm not going to go line by line in R and talk about it line by line. It's called 5 Class R text. It's based on chapter 9 of the text. This script is more or less in the online in the book website. I'm first going to set my personal working directory. And then I'm going to read in a table using read.table. I'm going to read in sort of a slightly obsolete extragalactic data set called Combo 17. It's 17 dimensions of photometry of many thousands of galaxies. At the time, it was very important, this data set. And I'm reading it in from our book website. So I must be reading it in now. I'm still busy doing it. And you may be doing it as well. Fill equals true means that maybe there's some terminal columns that are empty. Header equals true means that the first line tells me the data set, the variable names, and the LOZ is just low redshift. I just happen to choose some subgroup of the larger data set. Okay, so when this comes in, I think I'll probably skip the next few lines. I have the structure of that. We can take a look, the dimensionality of it, how many rows and columns, the names, the columns. And in this case, I added some names that were missing or something like that. And this is just an assignment of a variable. Is anyone else doing better than me? Are you still stuck like I am? Oh, that's because I'm not on the web. I was asked, am I going to use the web? And I thought not, but I forgot I am. Yes. Thank you very much. Okay, just excuse me 1 second. That's my problem. I'm not a Harvard guest yet. My apologies. No, I have an error. No, I'm not a Harvard guest. I have to be a Harvard guest. This is my problem, not your problem. There we go. Now, providing I'm nice, I now have web access. Okay, let's leave that there. Do an up button. I'll read. Oh, I read it in a fraction of a second. Okay, thank you very much. I'll make my names. And now I might as well just plot my data. In this case, I've only taken 2 dimensions out of 17. It's a color magnitude diagram of galaxies in some field. Who knows what a field it is? So there it is, absolute magnitudes versus color. I've made a 2-panel figure. And you can sort of see there's some structure there. It doesn't look really like a multivariate a normal. And actually, you're going to see that actually one of the best classifiers I have is just a kernel density estimator. The same one we saw on Wednesday when we did what's called density estimation. We're just going to smooth it. So there I did KDE2D, which you've already seen before, and I'm going to image it because it's now a grid, and you've seen that before, and I now have it over here. And actually, this is quite interesting. These features were published in the 1990s as major results of extragalactic astronomy. This is called the blue cloud, that's called the green valley, that's called the red sequence, and those are called bright cluster galaxies. And this is modern observational cosmology and galactic astronomy. And people discuss how do galaxies evolve across the green valley, and it's a very interesting field. So I just want to show you that one form of classification is just smoothing the data. It doesn't always work, and it certainly would be harder in 20 dimensions than it is in 2. Okay, I can, here. I can save that as a PDF, that image, and as a PDF with device, copy to PDF, dev.copy to PDF. Another rather useful thing. Now, yes, ma'am.
So when you smooth the data and you see this two peaks, is there a way to actually...
No.
So it's by...
No, it's unsupervised. There's no statistics. If I assume they have a multivariate normal, I could do that. But if I don't assume it, there's no way to do 95 percentile confidence of anything.
So it's just by eye.
You have to guess your way forward. And you're going to see it's going to be really crappy when I use the methods. Okay? So one thing to recognize is that in this particular case, the range of my variables are fairly similar. This range here is about 10 magnitudes. This one's about 5 magnitudes. But in principle, this could be kilometers per second, and this could be ergs per second. It had completely different units, completely different ranges, and the methods use the numbers. They don't know anything about the units, the physical units. So if the ranges are very different, it screws up the classifiers. So you almost always want to bring them to a common scale, and the way that this is done by statisticians is called standardization. You take x sub I minus x mean for each variable. You find the mean, and you move all of them to zero mean, and you divide by that variable standard deviation. So they basically run from -1 to +1, or minus a few to plus a few, if they're Gaussian. And so this happens to be our function scale happens to standardize variables. And so that's very, very commonly done. In fact, it's required that you do it. That you don't have the range of units be your major source of a criterion for classification. So here's the help file for scale, just to give you an example of a very generic function in R that is not commonly done in astronomy. We tend to take the log of things and assume everything's fine, but we don't realize that hierarchical clustering will depend on what that transformation is. Okay, now I'm going to do something nicknamed Friends of Friends, but not quite. I'm going to use a complete, rather than single linkage, hierarchical clustering. Friends of Friends gives real garbage in this case, and even complete doesn't do a great job. But you'll hear that later on this afternoon about the problems with Friends of Friends algorithm. And I've just made the tree. It's a distance in p-dimensional space. So here are my thousands of objects, and here's my tree. It's also called the dendrogram, which means tree in Greek, I think. All of them are on top in one big lump, and here's every single one as an individual twig, and these are branches, and those are trunks. And so it looks to me like I've got two clusters, and I'm pretty sure that that's going to be my red and blue. And I go and I cut the tree there, and I found that it wasn't true. So I went down to 3, and it wasn't good. 4, I had to go to 5 before I finally got one I sort of liked. So here's the cut of the tree with 5 clusters. It's in red. So I got an outlier here. I got a big cluster, 2 small clusters, and another big cluster. And then I'm now going to, quote, cut the tree, and I'm going to plot the cutted tree. What I'm doing here is I'm taking my symbol, which I usually put 20 for a solid circle. Then the symbol is now going to be the output of the tree, of the cut tree, the classification. So I'm going to sort of plot them by symbol, and you'll just see that in just right now what comes out. So there it is. Now, in this case, I did my calculation with standardized variables, but I happened to plot it back in the original ones just because it's familiar. And there it is. There's my red sequence, my blue cloud, my red sequence. But look at that. Those two are sort of their own cluster. So those are outliers. They're unusually blue, low luminosity. Hey, sounds like dwarf galaxies with star formation. Anna Grable talked about them, So maybe those are mistakes, or maybe that's a science paper. Okay, so at least the method told me to pay some attention to those two. Okay. Also, there's some diamonds on top that are sort of the opposite. They're unusually red. And there's some squares over there. Those are my bright cluster galaxies. And so this is not the world's worst classification. I certainly might learn something from this. But notice I just had to make up my algorithm, what's called complete linkage, and I had to make up k equals 5. And so it's not really its own personal definitive approach to things. Okay, I'm going to go to Ontario. I'm going to install a package. Please feel free to choose a mirror somewhere in the world and install your own package. No, it works. Okay, there it is. 400 kilobytes. Notice that most packages is just a little bit of R scripts. A couple hundred kilobytes or whatever brings it a whole capability. That's because that package called 5 other packages. And each one is calling many R functions that exist. And there's tens of thousands of R functions if you add them all up. And R, base R, maybe hundreds to thousands. And so it's very compact. What you need is the skill to write this package. And you and I, at least I don't have the skill. This is done by a computer science group somewhere that has the knowledge and the skill to do in this case to code up what is called density-based clustering. DBSCAN. So DBSCAN is one of the most widely respected density-based classifiers, and it comes from probably originally an IEEE journal. Yes?
I have a question about sort of using R in a kind of practical sense. So if you have the packages installed, then they will load. But if you don't have the packages installed, how do you find out which,
How do you find out what you want? Good luck. The answer is you can't. You have to become educated to know what you want. Once you're educated, and Wikipedia and my textbook are examples of elementary education, and Ivicek's book, elementary, and then you may learn more by reading other books. I just use Google. I look for CRAN, density-based clustering, and I go rummage around and find a few packages. There's the CRAN task views that summarize them. Someone's keeping track of them in clustering. There's a task view on clustering. And you find it in a heuristic fashion. I'm sorry, R is growing exponentially and disorganized and has no company. There's no index to the 100,000 functions. It's really a problem. One of the biggest problems with R is it's so big, and this sounds rude, and we're so ignorant. And the combination of our lack of knowledge and the hugeness makes it a big problem. So that's why I wrote the book. That's why I'm here today, to give you a sense of how you can proceed. To use more sophisticated methodology, you first have to know. That's why I give a lecture first. You don't do coding before you know where you want to go. You have to think ahead of time. Okay, let's take a look and see what DBSCAN did. I haven't used the print function very much, but you can print some results. That wasn't particularly useful. It says I have 572 points, and I used a range of 5 and something called an epsilon factor of 0.1. I probably rummaged around, fiddled to get a nice result. So again, for unsupervised clustering, there's a lot of subjective choice of parameters. And there's some plotting of points. Now I'm going to plot points with different clusters in different colors. And there we go. I got my blue cloud. I got my red cloud. And the advantage of density-based clustering is it allows you to say, and there's some points that don't belong to any cluster. That's actually a disadvantage of some traditional clustering techniques, is they insist that every object be in a cluster. And this is not true in this case. So then I said, well, frankly, I think it's a little too small. Can you make the blue a little bigger? So I changed the parameters. I got it. You know what happened? I jumped over the Green Valley, and it all became one cluster. So do I like this? I don't know. frankly, I sort of like my original smoothing. But I did a reasonable job with hierarchical clustering, but I had to fiddle. It's hard to publish the membership of these things when every time you fiddle with the parameters and the methods, you get different results. So I just wanted to give you a sense that unsupervised clustering is maybe useful, but is a dangerous enterprise as well. So all these classifications that astronomers have been doing, I mean, some of you do this. Is it a type 1a supernova? Or is it a type 2 peculiar supernova? It's not easy. You're using your mind, and it's not easy for unsupervised tools to do it. But if you have training sets, things get better. So we've now entered to the group of the rest of this hour is going to be classification, which is classification means supervised classification. That's the meaning of the term classification. It has training sets. So now I'm going to grab, and because we don't have a lot of time and because it's not particularly interesting, I'm going to grab a whole lot of R scripts from our Appendix C of our book that is going to grab 3 pieces of published, processed Sloan datasets that give, I pre-packaged the files. I got them from the ADS. So I'm at Harvard Smithsonian. We're the home of the astrophysics data system. I'd like to just set, it's wonderful, with all these electronic tables from all these journal articles. It's so easy to do things in astronomy. So I'm going to first bring in a test data set called SDSS_test. It's my own personal name. And there it is. So what I've actually done, you'd have to read my appendix to figure it out. But what we actually did is we asked, Sloan, please give me some, I forgot, 17,000, some fairly large number of point sources. Sloan point sources in some part of the sky. And I'm only interested in photometry data, so give me UGR IZ photometry. 5 dimensions of photometry from Sloan, which means 4 colors. Plot 4 colors and 3 bivariate color-color diagrams. Very common thing astronomers do. So there we go, color-color diagrams, and this is the Sloan point sources. This is not new, of course. This has been known since the beginning of Sloan. Okay, this is it. So you can immediately see that there really is some classification to be done. I mean, there's that snake, and it has a funny curvy tail, and then there's a clump there, and it seems to have a tail, and when you turn it around and look in other dimensions, some of them land on top of each other, and here they're all blobbing together. But it's pretty clear that this is not a homogeneous data set. Okay? And you can do this with the old IRAS catalog. You can do this with the RAS catalog in X-rays. You can do it many, many, many times, this kind of heterogeneous survey where you just know that it's heterogeneous.
I have a question. You're doing 3 sets here, and you have, I guess, 3 different data sets that are...
No, this is one data set in 5 dimensions.
Sorry, 3 different magnitude colors. You have
5 colors.
You have 5 colors.
4 color indices.
What if you take like 3 of those colors? I mean, can you do the same thing in 3D?
Sure. You obviously have less information. Sure. With Combo 17, they had 17. I only showed 2. So yeah, sure, you can do what you want. No one's forcing you to use all your data, or it depends on your data set. Yeah. Okay, so here's where I take advantage of this. A group led by Donald Schneider has spent years taking the Sloan survey and doing spectroscopy and identifying quasars. So I pulled in some quasars, a training set of 2,000 quasars, and you got to read my R code. I pulled in certain columns using I found some bad photometry. I had to filter it with some bad photometry, and then I got rid of the bad photometric data, and then I made my color indices using column binding and subtracting different columns, and then I I made it into a data frame, and then I put names onto the columns, and I set the final column to be just a bunch of ones using the rep or repeat function. So I basically now have a data set with 1, 2, 3, 4 color indices, and then a column of ones. And those are quasars. I then went to another paper. This one was by Zlatko Ivichik, and found that he had identified a bunch of stars. So I chose 5,000 stars from his electronic table, and I called them class 2. And then a certain young gentleman at the time named Daniel Eisenstein actually did white dwarfs before he discovered the BAO and became a Harvard professor. So Eisenstein has a lovely white dwarf paper in his youth with Sloan, and I took his paper and made a training set of white dwarfs, of 2,000 white dwarfs. And then I combined them together with an R-bind, row-bind. I just put them in one big column, one big row, and then I'm going to make a new device, a new graphics window. Let's see the new graphics window. That shouldn't take long. There we go. That was funny. Okay, and now I'm going to plot up my training set. So my training set, I can put colors on it. I know that my white dwarfs, I'm going to color my white dwarfs green. And I'm going to color my quasars black. And I'm going to color my stars red. So if you don't have a training set, you can't do supervised classification. But if you do, wow, it's great. You'll see it's just fantastic. Okay? So sure enough, it ends up that tail belongs to the stars. Those are the A and F stars. Those are the G, K, and M stars. The quasars are black, but the high redshift quasars are over there on the left. By the way, that's also where they found the T brown dwarfs. The white dwarfs are over here. They're mostly blue. They do overlap a lot with the quasars, but they're distinct. But there's a tail of red white dwarfs that go drifting off in other parts of the diagram. And so it's rather interesting and rather confusing. Even a single class is not multivariate normal. There's nothing there that looks like a multivariate, like a Gaussian. So we really should not be using any parametric methods. We have to use the data themselves, the training set themselves, in a non-parametric fashion to classify. Okay, so thank you very much. It took me a while to write that script, to read 3 papers and package them in together, but I did it, and it's the sort of thing that the grad students spend their times doing, manipulating data sets, and that we got to do that in astronomy. So I wanted to actually show it to you, the fairly boring part, non-statistical part of manipulating data sets. I don't have k-means. I would have thought I'd have k-means. K-means is in stats. I should have k-means. Error. I didn't clean up my NANs. Oh no, this will take a long time to fix. This is odd. I thought this was all okay. No, I can't just do anything with NAS. There's a lot going on. Okay. I've got 201 NAAs. Okay, let's see if I can do this. No, don't interrupt me.
Before you,
Yes?
there's a question from one of the webcasts.
No, I can't deal with it now. Didn't work. Oops. na.omit object. It handles vectors, matrices, and data frames. Well, should have worked. Ah. Okay, I got rid of from my test data set. Let me get rid of from my training data set. na.omit will get rid of I got rid of it. Now, hold on. I'm really upset here. I'm supposed to know what I'm doing here. Oh, it worked. Okay. So I had left in some missing data, it's called. In other words, I have a huge table of thousands of rows and several columns. And I left in some ... some missing data, no data things. So it ends up some of our functions deal well with missing data. They even give you an option. What should I do with it? And some of them don't. And since it's all written by different people, you can't predict what any function will do. So I won't claim it's the best thing to do, but what I just did is I just got rid of my entire rows that had missing data of any type using this command here, na.omit. It's a function. And I applied the function to both my training set and my test set, and I redefined that, and now I've cleaned them up so they don't have missing data, and I do apologize that I didn't do that ahead of time. I just messed up. But having done that, my k-means now worked. So I'm out of my crisis, and I can answer questions. So yes.
So this is actually from one of the webcast viewers. So the question is, so the training sets must come from somewhere, presumably from unsupervised classification. How does one iterate to reclassify the training sets?
Oh, no, I wouldn't use training sets from unclassified classification because it's incredibly unreliable. You have to do training sets of things you know about. You and your predecessors in studying white dwarfs and quasars and stars have studied stars and quasars and white dwarfs in great detail, and they have established training sets. If you don't have astronomers who've worked ahead of done studies, you don't have a training set. And you're stuck with classification. There's no bootstrapping that. You can't make it up. Okay. Now, fortunately, we have a century of astronomy before we do surveys like DES. So we actually know a lot about galaxies and stars and quasars. So we often have training sets. And that's why I'm teaching you or introducing you to some methods of supervised training, supervised machine learning. But if you don't have a training set, you can't do any of this. Okay? And you're left with a very unfortunate business. Okay. Yes, ma'am. Yes, sir.
Yeah, and is there a way to estimate how reliable is the result?
Why don't we look at that in just a minute? Okay? So thank you very much. Okay, so here's an example just to show you how unsupervised training did. It made a stupid caterpillar of methods out of the star, of classes out of the stars. Completely silly result. That was k-means. And this, by the way, this picture appears in a statistics textbook because they use a standard method of unsupervised classification, and they didn't realize this is really, really stupid result. He thought it was a good result. I don't know what he thought. Okay, he didn't know any astronomy. Oh, very frustrating. An advanced machine learning textbook, multivariate analysis and classification textbook by Eisen Min from Temple University. It's a good book in many ways, but not that particular figure. That particular figure was not very good. Okay, so let me now do something that I think might have a chance of being somewhat better than that. So this time I ran LDA, linear discriminant analysis from the 1940s. R.A. Fisher came out of his grave and told us what to do analytically. And you can see that it took planes, sharp edges, and it took the A and F stars and put them in with the white dwarfs. Why don't we just say that's really not a very good solution? You know, I mean, it's pretty obvious compared to just visualizing the training set. It used the training set but it didn't really do the best job. That's because LDA is a rather old and primitive method. So let's look at k nearest neighbors. It's a very simple algorithm. It simply says, for each object in my test set, let's take that one there, I then say, what are the nearest, let's just say, what do I have for k? 4 neighbors in the training set. And if the nearest 4 neighbors, I should have chosen an odd number, should have chosen 5 neighbors. If they vote, and if 3 or more of the neighbors vote that I'm a quasar, then I'm going to assign the new object a quasar. And it doesn't matter about the weird non-Gaussian distributions. K and N is just like a voting procedure. It's like democracy. Okay, it's really simple, and frankly, you'll see it works pretty well. So I had to bring in a new CRAN package, a classifier one, and now I've run a KNN classifier on it, and I got this particular result. And I think it did better. Surely it didn't make the A stars into white dwarfs. And those are the not so many white dwarfs, not many green dots. And it even put a green dot there and there. You know, it's sort of interesting. You know, made some black ones there. You know, I actually thought that looked pretty good compared to the training set. And actually, I realized later that this one's vulnerable to how many objects I arbitrarily chose to be in the training set for the different classes. Because if I chose an infinite number of white dwarfs, it would always win in that area, and not the quasar. So actually, it's not the world's best method. It's extremely simple, conceptually and computationally. I don't know if you know, but KNN is used by computer scientists everywhere because it's so computationally simple and even fast. It's used for image analysis, and it's used for many, many, many purposes. It's embedded in other algorithms in very nice ways.
Do people ever extend that to just assign probabilities of different classes?
No.
It seems kind of obvious.
Yeah, you'd think so, but I want to say I don't know. Any comment? Generally, there are no probabilities in anything I'm doing. Nothing, because there's no parametric modeling. It's all non-parametric. What I do instead, to answer your question, and essentially your question, is I got to go back. And so the simple thing I did here, which is actually not the correct one, but it's very simple, is I simply applied the classifier onto the original training set. And this is like a redundancy. You know, it's like a logical circle. But if I can't do a good job on its own training set, then I obviously can't do a great job on the test data set. So here we can say the black splotches means they got the quasars right, I got the white dwarfs right, the stars right, and I got the white dwarfs right. But you can see some white dwarfs got erroneously classified as quasars, and some quasars got misclassified. But not many. It's more than 99% good. The correct thing I should have done, and I'll do in the second edition, is something called cross-validation. I'm supposed to take some of my training set and put it in my pocket and not use it, and then use it afterwards for validation. Okay? So this gives, you're able to say, 99% of the time this aspect of the classifier is right when applied to the self cross-validated training set. That gives you some probability. Okay. But it doesn't really tell you, your test data set right, but at least it tells you something about your training data set. So it's not bad. It's certainly better than unsupervised clustering. Okay, let's see how a neural network does. In this case, I've chosen a very simple, probably inadequate neural network. I chose a single layer neural network. I ran a program called Multinome from a library called NNet. There's many other libraries I could have chosen, CRAN packages. And I don't claim I even tried very hard. KNN's so simple, there are no options, but neural networks is little gobs of options of how to do neural nets. And here's a neural net result, and the neural net did, in this particular case, a lousy job. It definitely did a lot of misclassifications. Okay? But I don't claim I did a great job. I just wanted to show you that I can do it pretty fast. And I did do it pretty fast, but I didn't do a great job. So now I'm going to run cart. Classification of Regression Trees by Leo Bremen with algorithm 4.5, I believe I'm using here. It's called recursive partitioning in R. Oh, that's because Bremen copyrighted the word cart. So R is not allowed to use the word cart. So it's called recursive partitioning, which actually is a formally correct thing to call it. And I use the predict function quite a bit here to apply it to itself and to the other data sets. Predict is used not only for regression but for classification. Summary told me, here's a structure. Look at the complicated thing that came out. Oh my goodness! Of the list file that comes out is just incredibly complicated. So these are not simple programs. They do not produce simple results, but you can plot simple results if you choose to. So here is a plot of the performance of the cart. Okay, so I would say it did not a very good job. Okay. This is now, it makes this, well, I'll show you the decision tree in just a second. It basically took the A stars and put them into the white dwarfs again. And it put some white dwarfs way up there in the M stars, which I thought was really peculiar. And also the quasars started eating away on the G stars. This was really not a very good solution. Okay, so this particular card, I could manipulate the parameters of card. It has lots of knobs in it. I don't claim I did the world's best card. All I want to say is this is an example of what I could do. Now, what is useful is to actually look at the tree itself. And here's the tree itself. It's a little scrunched up there. Well, I'm sorry I don't have a nice view of the tree. So, but this is interesting. The astronomers can understand this tree. It's not black box when the result. The first most important split was G minus R has to be greater than minus 0.04. And that split it into two parts. And then the next one was U minus G has to be less than 0.35. And then it split and split and split. And then it actually knows not only how to split in a mathematically defined way from some Gini impurity I think I used, but it even knows how to prune it back up and not make too many splits. It tells you, it knows how many splits are important. And this is just the simple version. And if I did boosting and bagging in random forests, I'd be able to jiggle the tree and simulate the tree and help consolidate things and know which one of these branches are reliable. By the way, the class 1, class 2, class 3 does not, it's not that all of those are 1 and all 2 and all 3. In principle, class 1 can appear in different twigs. And that allows very complicated structures to be modeled really quite well with random forests. But unfortunately, my particular application here was not particularly good.
Question?
Yes?
So it seems like it's making planar cuts through the space. Is there
Yes, this one not only is planar, by the way, linear discriminant analysis was a tilted plane. Okay? This one's actually planes only parallel to the axes. That's a decision tree. That's decision tree are planes parallel to the axes. That's the same thing. So this is a method. It's not the only method and not necessarily the best. It's actually fairly good for many things. Okay, I just didn't, frankly, do a great job here. I didn't work on it on purpose. I wanted to show you that, you can get, it's like I would say it's not like playing a symphony by Beethoven. It's like jazz. Okay, you have some structure and you learn how to play your saxophone, but it's an art to do classification. You're sitting there thinking, wow, I bet my support vector machine capability with certain options is going to really help me do this part of it. Okay, and then you do validation at the end of it. And say, oh, wow, I improved from 99 to 99.5. I improved my performance. And so this is what computer data analysts do. They get trained in computer science departments in machine learning. This is also called machine learning classification techniques. They then get hired, typically by companies, to analyze large multivariate data sets and find classes and then do regressions and find structures within classes. And they present it to middle managers who then make better products or better services and make money. this is done. I wouldn't be surprised if this is run 10,000 times a day in America. Victor, more or less? Okay, thank you. So astronomers never do this. I mean, it's done occasionally. And the kind of thing is that, well, for instance, some astronomers 15 years ago found neural networks, and all they do was neural nets. Well, frankly, neural nets are really good for some problems and sort of stupid for other problems. And LDA is good for simple problems and really poor for others, but SVM is really good. SVM, support vector machine, is the Vapnik's generalization of linear discriminant analysis. And I just ran it. I didn't show you, but it actually took like 20 CPU seconds for me to do the SVM here. This particular program was computationally intensive. Okay, what do I have? 10,000 points or something in 4 dimensions. It actually took some CPU seconds. Everything else was like lightning. So that's an example that SVM is a serious computation. Okay, let's take a look and see what SVM did. Oops, sorry. There's my SVM classification on this particular 2-dimensional plot. And I said, oh, that's pretty darn good. It got the A and the F stars to be stars. I'm glad. It got the quasars to be here, and it got one high redshift quasar over there. And over there, it decided that one of those was a white dwarf and one of those was a quasar, which is a hard decision because they each sparsely populated up there. And it's really hard to know. And then it didn't do very many white dwarfs. So let's see how it did. I think there's a problem. There's a few red dots in here. It classified some things in the quasar regime as stars, and that's probably what I'd call a mistake. So let's see. Here it is on top. We want the 1s to be 1s, the 2 to be 2s, the 3s to be 3s, and in this case, they're actually intermediate classifications, and that's the way it is. And you can see that it did a pretty good job, but this is 99.9% correct. It did a really good job. Support vector machine did a really good job. Okay, so let's say I'm finished. I'm ready. I've done my jazz. I performed in the club, and I'm ready to publish. So I'm now going to apply it to the full test data set. My support vector machine is now fully applied. I plotted all the dimensions. This is what I'm going to publish in the Astrophysical Journal. Okay? Those are quasars, blacks. Those are white dwarfs. And those are stars. And oops, I have a few mistakes. It's only 99.5% right. Sorry about that, guys. But I did my best. Okay? So how do you get things out? You have everything I've done has been within R. So now I'm just showing that you don't have to stay in R. Whoops. Oh, I have one thing that's 8,086 lines and another thing that's 8,085 lines. You know, I'm not going to solve this problem now, but this is very common. You know, the stupid missing data problems, the stupid vectors that are off by 1 unit. Oh my goodness, I'm frustrated. Okay, but what do you do when you're a grad student or a postdoc or a professor? You spend your time on the hassles, you know? So I'm not going to solve this. But what I wanted to say is you can write dot table, the original data, and the output classification as a column. And now I have it there as a table ready to be studied, published, or studied with Python or anything I want to do with it. So I can bring information, results, out of R, even though I lived inside of R to explore the data and to try out methods. Okay, yes, sir.
So the question I had was the question I had was, as we're running some of these things, our classifications of the SVM, the published version, looks different than yours.
Oh, I don't know. Sorry. It should be the same, but you know, my read dot table of the data set may have been wrong because something's wrong with my internet. So it should be the same. Okay. Sir.
So what if I did the stupid thing the old astronomer would do, which would be to take the multidimensional space and draw intelligent curves that went through them, because I know that the stellar locus, for instance, is curved, how much worse would that be than just doing it this way?
I have no idea. This is a question in the philosophy of how you want to do science. I'm not saying it's wrong to be heuristic. All I want to say is it's not a mathematical, quantitative, or objective procedure. So you would have, okay, I'm sorry, I'm a little old, but you would have Gerard de Vaucouleurs say, well, that's an SAB parenthesis RS galaxy, and you would have Sidney Vandenberg say, no, it's an SBA parenthesis P galaxy or something, and they would argue. So they neither had mathematics, and in that case, more form of galaxy morphology was very subjective. In fact, even today, we don't have good ways of doing galaxy morphology objectively. So it just depends on how you want to proceed. Obviously, for an easy problem, who the hell needs fancy methods? So also, when you have a petabyte, you can't even use heuristic methods.
Maybe one can link the two words. If you have a training sample, you can try to do it this way and see what happens at the training sample.
Yeah. You have to have known the classes of every object in your training set to begin. If you don't have a training set, you can't use any of these methods.
No, but even with the old methods, one can just draw the lines,
Okay.
and then apply to the training.
Right. You can do cross-validation on the heuristic methods. You can cross-validate anything. Right. Yeah. Cross-validation is very much like the bootstrap. Bootstrap was this just clever idea of how to resample data with replacement. And then they wrote theorems, pure math theorems, very difficult theorems, that says the bootstrap's incredibly good in many situations. And then cross-validation says, hey, put 10% in your back pocket and check it out later. It sounds like a great idea, reasonable. And they wrote theorems that said cross-validation is a very powerful way of evaluating things. But there's another theorem. Go look it up in Wikipedia. Type in no free lunch theorem in Wikipedia. So I have no idea how they wrote the theorem, how they could do this. But they said if you don't have a training set and all you have is a data set, there's no way to evaluate which one classifier is better than another one. No free lunch. You're left wandering around in methodology world, lonely, like waiting for Godot. Okay, so it's great, it's wonderful. They actually know when certain procedures work and certain don't, even if they don't, you don't have probabilities associated with them. So there are things in theoretical computer science, theoretical mathematical statistics, that are results that can guide you. You're not. You actually have some things you can learn, and you read Ivicic and Feigelson Bamboo to give us elementary entree to it, but you really should be reading books on machine learning if you really want to do this kind of stuff. By the way, there's 100 books on machine learning, so we tend to guide you with some books we liked. Okay. Well, thank you very much. I'm only 8 minutes late. I think we should take a 5-minute break, and we'll come back, and I'll do a somewhat shorter presentation on spatial point processes, so we might even end up on time. Okay? Good. Thank you very much. See you in a few minutes.